Come on in and don't be late. Let's learn science with Mr. Ed U Cate.
Okay, so in this section, section 3.5, we're looking at the Bronsted-Lowry model. And I just wanted to mention that my little pointer here, I couldn't get an arrow, but I've got this little doodad circling the screen here. I just want to let you know that I'm always going to be tracking under what I'm talking about. So the Bronsted-Lowry model, if you know what I mean. Okay, in this section here, we're looking at that model. It's an updated model. It's a more accurate model of the relationship between acids and bases in equilibrium. Don't forget, it's in equilibrium. It does apply to acids that fully dissociate, but in particular equilibrium. And we're going to illustrate the transfer of hydrogen ions between conjugate acid-base pairs. We're looking at amphiprotic acids or amphiprotic species. A species, by the way, is just a chemical. And we're looking at some of these chemicals that can act as both an acid and a base. And we're going to identify and deduce the formula of conjugate acids or a base of any Bronsted-Lowry base or acid. Okay, should be fun, fun, fun. Well, we learned about Arrhenius acids at the end of last year. Arrhenius acids are just simply a definition for an acid, and they are a substance that give off hydrogen ions in aqueous solutions, whereas an Arrhenius base, they give off hydroxide ions in solution. Okay, the problem with this theory is that it is limited. It's good in a lot of circumstances, but it doesn't work for all acid-base reactions in water. Then along came Johannes Nicholas Bronsted and Thomas Martin Lowry in 1923. They came up with the Bronsted-Lowry model for acids and bases. This model defines acids as any species that can donate protons, and bases as any species that accept protons. So we talk about the concept of a proton donor. An acid is a proton donor, and we talk about bases as proton acceptors. Okay, so I remember you guys were tricked up about this in class. Don't have to be too worried about this concept. All we have to know is that a conjugate acid is an acid formed when a base accepts a hydrogen ion, and a conjugate base is when a base is a base formed by removing a hydrogen ion from an acid. The only thing tricky here is if you look at the definition without an example, but in every situation, in every equation, any acid plus any base is in equilibrium with its conjugate base and conjugate acid. The acid donates its proton to the base, and when that acid loses its proton, it becomes a base, the conjugate base. And the base, when it accepts the proton being a hydrogen ion, H+, when it accepts that hydrogen ion, it becomes a conjugate base. Nothing tricky at all. It's a bit like, what did we look at last year? It's a little bit like redox reactions with the donation and accepting of a electron. One of these two reactants gives the proton. When they give the proton, it loses it. So the acid loses the proton to become the conjugate base. And it's a reversible reaction, remember? That conjugate base can get that proton back to become the acid. So if we have a look at an example here, okay, don't forget we're looking at page 87 of your textbook. Let's have a look at this example here. The ammonium ion, NH4 plus, is the acid, and we've got a hydroxide ion, which is obviously is the base. They react to each other, whereby the ammonium ion loses the H plus ion to become NH3. Can you see that? NH3 is just the same as NH4 plus, but without the proton, without the H plus. That proton, that H plus ion, must be given to something. Like last year, you can't have oxidation without reduction. Well, you can't have an acid-base reaction without one without the other. The acid gives the proton to the base. Okay, so the NH4 becomes NH3. When the OH minus, the hydroxide ion, accepts the proton, it becomes a water molecule. So that was the acid, the NH4, the ammonium ion was the acid. It becomes the conjugate base. The base in the reactant becomes the conjugate acid. This is reversible. So the water can give up its proton, it gives it to the ammonia molecule, and produces these two. So basically it's like that. Let's go to the next page. So all of this here is just talking about what I just said. You can just read about that in your from your textbook. So how do we identify conjugate acids and bases? Let's have a look at this different example. This is not a reversible reaction. This is not an equilibrium reaction, but still, you can still illustrate conjugate pairs anyway. Oh, and by the way, conjugate is a word that means join. So if you're tricked up by the word conjugate, don't. It simply means join. For example, in this acid-base reaction, this one here is nitric acid. Aqueous nitric acid reacts with liquid water, just dissolves in water to produce a hydronium ion. Don't forget, most acid molecules is actually in the form of a hydronium ion, H3O plus. We just shorten it down to H plus. So the nitric acid loses its proton to water to become H3O plus, and the water what am I talking about here? Sorry, here we go. The HNO3, the nitric acid, loses its electron to water. Water, when it gains that H plus ion, the proton, becomes a hydronium ion. The nitric acid, because it loses its proton, becomes the nitrate ion. That's the nitrate ion there. So really, all that a conjugate pair is tracking where each reactant, what happens to each reactant. The nitric acid molecule is nitric acid over here, but what becomes of it over here? It becomes the nitrate ion. So the nitrate ion and the nitric acid molecule is a conjugate pair, is one conjugate pair. The water molecule here is paired up conjugately with the hydronium ion. One conjugate pair, another conjugate pair. That's all there is to it. Okay, so you could read about that there that I talked about. And in table 1, it just shows you some common Bronsted-Lowry acids and bases and their conjugates. For example, hydrochloric acid is the acid. Its conjugate base, when it loses its proton, is the chloride ion. Okay, the base that the acid reacts with is the hydroxide ion, and the conjugate acid of the hydroxide ion is H2O, water. And then we come to the topic of amphiprotic species. We're now up to page 88. We've flipped pages. The word amphiprotic is a molecule or ion that can either donate or accept a proton, and so therefore can act as an acid or a base. So it's a tricky little chemical that can be an acid or a base, and the classic example is the hydrocarbonate ion, the bicarbonate ion. The bicarbonate ion can act as both an acid or a base. So here we go, we've got two reactions, this one at the top, this one at the bottom. In both cases, the reactants are exactly the same. Bicarbonate ion reacts with the water molecule. Bicarbonate ion reacts with water molecule. But there's two different pathways here. At the top, the top reaction involves the bicarbonate ion, losing its hydrogen ion to water. So when the bicarbonate ion, hydrogen carbonate ion, loses its proton, it becomes the carbonate ion, CO3 2-. Again, if you forget all these, the names of these common ions, they're in your data book. But it's good to recognise them straight away. So when the bicarbonate ion loses its proton, it's got to lose it to something. It loses it to water. So water gains that proton to become H3O+. In this bottom reaction, same reactants, but this time, rather than giving up its proton, this hydrogen carbonate ion actually gains an extra proton. And where does it get its proton from? Water. The water molecule here acts as the acid, giving up one hydrogen ion, so that the bicarbonate ion becomes carbonic acid. Okay, and when the water molecule loses its proton, it becomes a hydroxide ion. Okay, so in the first reaction, like we read here in the first reaction, by the way, I don't know if I mentioned this, commonly known as the bicarbonate ion, sodium bicarb in your kitchen cupboard is just made up of sodium bicarbonate. This is the bicarbonate ion. In the first reaction, it acts as a proton donor, but in the second reaction, it accepts a proton, so it becomes a proton acceptor as we go to the next page. So when does the bicarbonate ion act as a proton acceptor, that is a base, and when does it act as an acid, as a proton donor? Well, it just doesn't pick and choose when it does this. The bicarbonate ion acts as an acid whenever it's in a basic solution. So whenever it's in a basic solution, it wants to use up the hydroxide ions to make it less basic. So it gives off more, so it acts as an acid to push the reaction this way to the right, to use up the hydroxide ions. However, the bicarbonate ion, when it's placed in an acid solution, it acts as a base. So here we go, the bicarbonate ion acts as a base. When placed in an acid solution, it wants to push the reaction to the right here to use up the hydrogen ions, and to make the pH go up or less acidic. Anyway, we're going to tackle more of this stuff in the next section, section 3.6, when we look at buffer solutions. Well, let's solve a problem that you could encounter in an exam. Let's go for an actual question from Check Your Learning 3.5, and we'll have a crack at question 2. The question asks us to identify the two conjugate acid-base pairs of the following reaction. So they're giving us HSO4-, which is hydrogen sulfate, and that reacts with a phosphate ion, and that reacts to produce the sulfate ion. Again, you should be able to recognise these sorts of ions straight off. Phosphate ion, sulfate ion, the hydrogen sulfate ion over there, and hydrogen phosphate ion over here. And can you see it's not an equilibrium reaction? It just goes to full completion. Okay, so what have we got to do here? We've got to identify the two conjugate acid-base pairs. Well, first of all, what we've got to do is we've got to figure out what's the original acid and the original base. So that's really easy. The original acid and the original base is on the left-hand side. They're the reactants. And it's easy to identify the acid because it's the one with the hydrogen ion. This one doesn't have a hydrogen ion at all, so it's the base. It's the species that accepts the hydrogen ion. So over here, one of them must be the conjugate base and one must be the conjugate acid. Okay, so the conjugate base must be this one, because likewise, whether it's a base or a conjugate base, it can't have any hydrogen ion. It can't. It's the one that doesn't have a hydrogen ion, and so over here must be the conjugate acid. Just check that it's an acid. Yes, it is. It's got a hydrogen ion. So the reactants are always acid and base, and the products are always conjugates. Both conjugates, which one's the base and which one's the acid? Well, the base doesn't have a proton, the acid does. One last thing though, we often use brackets to link the two, and that's an easy process as well. We'll link these two first. Basically, it's easy to link the two that we want because the phosphate is linked with the phosphate over here. Okay, phosphate, the one with the P, not potassium, phosphorus. The one with the phosphorus here, one with the phosphorus there, you connect them with the square brackets. The sulfate ion containing compound here is linked to the sulfate over here. Okay, so don't let me see you linking, for example, if this was an exam question, linking the sulfate to the phosphate. Okay, it all makes sense. So this is one conjugate pair, and this is the other conjugate pair. So you've answered this question, question 2, on page 89, just diagrammatically, and it's perfectly legit for you to do that. You'll find when you go to OneDrive and you check the answer for question 2, for this Check Your Learning problem, they've written out the equation, but they've listed down what the acid, what the base, and its conjugate base, conjugate acid pair, partner. But I like to do it diagrammatically like this. But don't forget, the acid always becomes the conjugate base, and the base always react to produce the conjugate acid. I think that's the bit that messes with your mind, but don't let it mess with your mind. if you put it in the context of the reaction, it all falls into place. All right, catch you later, guys. Hopefully I'll be able to do this live pretty soon. See ya.